Okay, hello everyone. So this week's video is on some of the internals of how memory works in computers. And by internals here, I mean internals in the way the memory is made available to your computer program, not about how the memory works as a piece of hardware, not even about exactly how the operating system provides memory to your program, although there's a certain element of that in there. But more particularly, I'm going to be talking about the fact that you have two pretty much completely different types of memory that your program can access, one of which is called the stack and one of which is called the heap. So stack is something that we've mentioned before when we've talked about how functions work. And the stack, as far as memory is concerned, is very much related to that. So I'm just going to write a very, very simple program in C. And it's just going to consist of a simple function, which I'm just going to call fn, which is going to take an int, single integer, and return the same value incremented, or it's going to call itself with that value added, having 1 added to it. And I'm also going to create in here a temporary variable, which I'm going to call j and set equal to I. And then I'm going to create my main, my entry point, and I'm going to call that function starting with a value of 10. Now, this program you will immediately see is not a good program. This will just carry on, ignoring any other questions. This would never terminate. This is actually a classic example of a computer program that could never terminate, because this function will just keep calling itself with a larger number forever. But we're going to ignore that because I'm not actually going to run this program to completion, which it would never do. I'm not interested in running it to completion. I'm interested in seeing what will happen when I run it. So in order to do that, I'm going to compile it. I'm going to use this -g flag so that I compile it with what are called debugging symbols in. I'm going to run it through the GDB debugger. Okay. So what I'm going to do is I'm going to tell GDB every time it enters that function fn, it should break, it should stop, and it should return control to me. Okay, so if I now run the program, it runs, it starts, and it stops. And I can now type bt, and it will tell me that it's gone into main, and then it's gone into fn once. This number here, that's not the number I called it with. I think there's something up with the way GDB is working on this system, but never mind. I'm then going to continue, and it calls itself, and I get another break. The breakpoint triggers again, and I can now look at it again. It goes into main, into fn, into fn. And I can run it again and look at that trace, and it's gone main, into fn, into fn, into fn. There we go. Now, that is exactly what I said it was going to do. If I just let it run on its own, that program would just keep calling fn every time with a greater value of I. Now, the reason that I'm saying this is about memory, not about functions, is because I can also use GDB to step back through this list of functions. So this here is what's called the call stack. Every time I call the function, a new object is created, which is called a stack frame, that describes every time the function is called. And it's a separate one every time the function is called. And I can step back through these stack frames, and I can look at things in them. So if I go to frame 1, which is here, I can then tell GDB to print that variable j, and it tells me it's 11. Well, that is correct. At frame element 1, the parameter was 11, and j just equals that parameter. So that's correct. And I can now go up here to frame 2 and print j again, and it's 10. And this sort of gives you something about what the computer is actually doing behind the scenes here. There really is a different j every time that function is called. And that's because the variable j is part of the way the function itself is called, part of this call stack. So we talk about it as being the memory that stores that variable j as being stack memory. And essentially what that means is every time the function is called, there is a completely different version of j that is created, and I can step back and I can look at all those different values of j. Now in this program it's completely uninteresting and utterly trivial, but the fact remains that all of those different copies of j exist for so long as I am still in that function. Now this function will never end, because it will keep always calling a new one. But if I wrote another version that did finish, which I'll just do now. So let's put it in here, and I do in here if I less than 20, return fn I plus 1, otherwise return just I plus 1. So that is now a code that will run, compile, and finish. So I'll just confirm that by compiling it again, run it, and it completes. But I will now run it again through the debugger. And I'll put that breakpoint in again, and I'll run, and I will continue. I shouldn't have picked 20, it's far too high a number. Okay. I actually let the program finish. Let's set that to not 20, but 2. I can keep track of no, that'll be 2. If it's 2, I'd have to start there. 2, and I'll start with 0. That's the trouble with doing these things live. There's always mistake creeping. Okay, so I put in my breakpoint, and I run. Okay, started the thing. Okay, I continue. And I now have 0, and it isn't showing it right again, but I would have my 1. I now have my 2. And now what's going to happen if I run it again is it just finishes. And that was unhelpful. Okay, let me just say what the key element here is. The point is, as you call those functions and go into them, these stack frames are created. They contain information about the function. They also contain the variables in that function. And those variables are really there. They have their own individual values in every call to the function, which are there until the function returns. When the function returns, the stack is unwound, as a technical term is, and all the variables are deleted as well, because the stack frame is just destroyed completely and all the variables are held in there. Now, that works. It works brilliantly, and it means that in pretty much every programming language, just a normal variable, if you create something like int I or int j, as I did there, you don't have to worry about it. When you leave the function, your integer just disappears, your floating point disappears, whatever. This can create some unexpected results. Let me go back to this, and now instead of returning an integer, I'll return a pointer to an integer, and I'll say int j is I, and I will return a pointer to that integer in there, and I will now print the result here, put in the necessary header, standard I out. Now there's a decent chance that at this point, yeah, it's warning me. Function returns address of local variable. Yes. I forgot. I have to dereference that pointer there. So this is warning me the function returns the address of a local variable. And when I run it, I get an error. And the reason for that is because this variable is created only in that stack frame. Once this function leaves, that memory is gone, it's no longer meaningful, and talking about a pointer to that memory can do anything. It can produce nonsense, it can produce exactly the result you expect, completely unpredictable. So that is why you can't return pointers or references to local variables in general, because of this stack memory. So I said there was another kind, and There is. So this other kind is called heap memory. Now, I'm not going to belabor the point too much, but the names don't quite mean what you think they mean. The stack is sort of obvious. Things are built up. These stack frames are built one on top of the other. So it's like something stacked up. And there is also a formal data structure that we've talked about previously called a stack. And yes, they are related. Heap memory, on the other hand, is just, there's just this undifferentiated chunk of memory that your program has access to, and there's just stuff in it. It's just a pile. There is also a data structure called a heap, but it is not related to heap memory. So don't think too hard down those sort of lines. Now, I am now going to show heap memory. So heap memory is a little harder to use because you have to explicitly ask for it. And in C, that asking for heap memory is with a function called malloc. So I'm now going to create my int star j, and I have to explicitly say that I want something that's the size of an integer, because malloc gives me a certain size in bytes. Once I've done that, I can now do star j is I, so I'm dereferencing my pointer. I'm setting the actual value that j points to I, and I'm returning j. I now don't get a warning, and when I run the code, it works exactly as expected. So if rather than doing fun of 0, I do fun of 10 there. Okay, that's all working as expected. But there is a downside to this power. And the main thing about it is that unlike the stack, which goes up as you call functions and down as you leave functions, the heap really is just, it's a heap. It's just sitting there. It just sits there until your program ends. If you want to get rid of the memory again, you have to explicitly free it somehow. And you can actually see that problem happening. So if I create another function here, which I'm just going to call test, why not? And I just call actually I don't need an extra function for this one. Okay, so I'll just compile that, and I'm going to run this through another tool called valgrind. Almost everyone calls it valgrind. I'm doing a proper video here, so I'm giving it its formal name of valgrind. It's based off Norse mythology, but a lot of people think it's valgrind because it sort of works by grinding out information about the program as it's running, which sort of does. But it's a very useful thing, and one of the things it can do is it can tell you about lost memory. So I will run it, and it goes through, and it tells me I have definitely lost 4 bytes of memory. And the reason that I have lost them is because after this line here, this function returns a pointer to an integer. I use that pointer here, but I don't record it. So as a consequence, I no longer have any way of accessing this memory that I've allocated on this line, which means I have no way of freeing it, which means it is lost. It is what's termed a memory leak. So if I wanted to do it properly, just to show, I would do int star j here as well, and that's fun of 10. I now don't use that there, I use j, and I would then free j, which is the opposite of malloc. Free releases my memory. So if I now compile that, I should still have dereferenced that pointer. There we go. I can now run it. It still works, and I can now run it through valgrind, and it tells me all heap blocks were freed. No leaks are possible. So this heap, this is what I'm talking about. Big chunk of memory. I've used malloc to alloc memory on it, and I've used free to get rid of it again. Now, the key thing here is this distinction between heap and stack. is moderately well defined. In reality, on some systems, you can actually, allocate memory on the stack. Not every system permits this. Linux does on at least some architectures, but they actually recommend against using it. But as a general rule, this is sort of the way things work. If something has a known size, like an integer is always a fixed size on a given system, usually either 2 or 4 bytes, then it goes on the stack. If something does not have a fixed size, and you have to, when the code is compiled, like an array that you don't know how big it is until you've read a file or something, generally you will allocate that on the heap. This is all approximate, is all general. There are various ways in which these things break, but that's a good rule of thumb to keep in mind. But you don't actually have to do much until you realize that while that's pretty much how things work behind the scenes, things can sort of blur things together. Now, I'm going to show something in C++ and something else in Fortran here that sort of fairly neatly shows it. But the first thing I'm going to do is I'm going to create the same program that you just saw in C, and I'm going to create it in Fortran instead. Okay. So this takes a bit longer to type, because Fortran is a slightly more verbose language, but it is essentially the same thing. So I have a subroutine in Fortran now, which I'm going to call test. And I'm going to take integer I again. And I'm going to have another integer, which is going to be an allocatable. I'm going to call data. And I'm then going to allocate data equals I. Now, I'm not returning the pointer here. I will not bother because I've got test and test here. I'm going to call that test M for simplicity. I'm not going to bother with that because it does just complicate things for no real advantage here. Okay, and I'm going to use test M, and I'm going to call subroutine test with the value 14. Okay, so this is exactly the same thing. I am allocating here data, which is exactly the same as using malloc in C. That is what it is doing. It's allocating heap memory. And I'm going to compile this program. And I'm going to run it through Valgrind again. And it's telling me all heap blocks were freed. No leaks are possible. So what is going on here? Is this some Fortran magic? Is Fortran doing something special, something different? Is this thing, even though I'm allocating it here, is it winding up on the stack so it gets unwound? Well, the answer to that is no. It definitely isn't. What it is Fortran gives certain guarantees that are not intrinsic to the heap and the way it stores data, but are intrinsic to Fortran. So I'll just briefly show you I can, in fact, make Fortran break in exactly the same way as C. I'm going to create not an allocatable integer, but a pointer integer. That code compiles as well. That code runs, and now I have lost 4 bytes. And the reason that there's a difference here is because of the way Fortran works with memory. It still has this heap and stack difference, but Fortran knows if you have an allocatable value like that, an allocatable value can only be referenced one way, basically. You can have pointers to it, but there is one canonical thing that is the allocatable data object allocatable member. So the Fortran standard requires the Fortran compiler, when you leave the subroutine, to generate the code to deallocate this data array. And that isn't something that, intrinsic to the way the stack works. It isn't something intrinsic to the way the heap works. It's just something about the way the Fortran compiler works. And the Fortran compiler says, okay, if I have an allocatable value, an allocatable array, more usually than a single thing, I will deallocate it when I leave a function, exactly like it was a stack array, a stack value. And that's a very nice feature of Fortran. Pointers in Fortran don't give those guarantees. They're like pointers in C, so I was able to get the error back. Okay, so you might think, well, that's Fortran, bit of a niche language. It's a nice feature, but never mind. However, as it turns out, other languages do exactly the same thing, and most notably, there is a very similar thing in C++, where the idea is often called, or related at least, to the concept of resource acquisition is initialization. So in this one, I'm going to create a class, demo. I'm just going to make everything public in here for simplicity. And demo has a constructor. So you have a C++ class. This is called when the class is built. And for the moment, I'm just going to get it to print constructed when it is constructed. I need another include there, and I'm also going to put in a destructor that is called when the class is destroyed. Okay, so I'm now going to create a function which is going to be extremely dull because it's just going to create an instance of my demo class. And I'm then going to construct my main, which is going to call my function. Okay, I compile that and I run it, and it prints constructed and destructed. So that is what these lines are doing. When this is created, it calls a constructor, and when it is destroyed, it calls the destructor. Fine, that's probably something you're very familiar with. And that's happening isn't surprising. This is just a normal variable that is created inside this function. So when I go into the function, the stack frame is created, the variable is created, the constructor is called to build the variable. When I leave, the stack frame is destroyed, and as part of that destruction, the destructor is called. Now that actually, it's worth noting, is the same as what Fortran is doing. There is nothing in the way the stack itself behaves that calls that destructor. On its own, all the destructor would do would be get rid of the memory. Wouldn't call the destructor for your class, and that is something, again, that the compiler is producing code to do. But this then shows how you can have the nice properties of stack variables with their automatically controlled lifespan with the ability to have arbitrary sizes of things that you get from heap allocation. So if in this thing here I create an integer pointer, make it null pointer, and let's only create a constructor which takes an integer in. So it constructs, and then it does I is new int, yes, I called it I twice, let's call it CT for count. Okay, so new does basically exactly the same job as malloc in C, it's just C++ instead. Doesn't matter for integers, I could use malloc here, it's not good form in C++, but it would work. Okay, so here I am creating my integer, and here I am going to delete my integer. Now I have to change here because I can't just create a D now. I have to create a D with some value because I've only got a constructor that takes an integer as a parameter, but that will now work. And if I compile that code and run it through Valgrind, I have no leaks, despite the fact that I used a new here. And I can show, if I, for example, make this a comment here, colon. Okay, so if I make that a comment there, get rid of the delete, I have a memory leak again. I have lost memory. So this is essentially how behind the scenes things in C++ like vector, say, work. When they allocate memory, and they have a destructor that deallocates the memory. The vector itself is just an object like this that is created on the stack and automatically gets destroyed when the stack does, and as part of the guarantees a C++ compiler gives you, the destructor is guaranteed to be called in that stack unwinding, and hence the destructor is called, the memory is all cleaned up, and you don't get any memory leaks. Now, I will say this sort of thing, this resource acquisition is initialization, which is related but not the same as this. It's a very powerful way of programming if you are working in a scenario where you have to work with your own memory. I should say, as a good modern C++ programmer, you probably shouldn't be managing your own memory if you're not writing your own deep down data structures at the core of your code. Most things can be done and get decent performance out of using the built-in things like vector or dec or stack or various of the other C++ STL data structures. But essentially, this is how you get the benefits of both the stack and the heap. You use the stack to store a variable that has a well-defined lifetime. Here, just a simple object called demo. And then you use the existence of things like constructors and, most importantly, destructors to guarantee that that object allocates its own memory, which is done on the heap and potentially allows the risk of memory leaks, and guarantees that when that object is destroyed, that memory is released again. So that's basically it, a quick run through heap and stack memory. I will just say one final thing before finishing, which is a lot of languages use what is called garbage collection rather than these kind of memory allocate and memory deallocate things. In garbage collected languages, what happens is every object that you create of any type is somehow connected into a big connected tree of objects, generally at least, and as soon as an element of that tree gets cut off, it is then made available for garbage collection and deallocation. And that has some advantages. It means you don't have to worry about doing things like that, although I'd like to think that, as this example here shows, it's actually not that difficult to manage memory yourself, so long as you are careful about doing it inside encapsulated objects that have well-defined lifetimes and guaranteed to clean up their own memory. But the downside of garbage collection is you never quite know when the garbage collection is going to happen. You never quite know whether that's going to be in the middle of some process you'd rather wasn't slowed down by that code running and things like that. But that's basically it, and we'll be back with another video.